will be the last talk of the afternoon, as warned by the Heidelberg has just been cancelled. So we are pleased to have Yucheng Liu from the University of British Columbia. The title is...
Thanks for the introduction. The title of my talk is Continuous Time Weakly Self-Avoiding Walk on Z has strictly monotone escape speed. So this is going to be a one-dimensional thing. So let me start with the problem. Let's start with the discrete time weakly self-avoiding walk, which is a simpler model to define. This is a model based on the simple random walk. And basically what we do is just that we just penalize self-intersections. So given a discrete time walk xn, we should penalize using the local time as certain point x up to time n, just by counting the number of times I have been in that position. And then with that definition, if I look at the sum of squares of the LNs, this is some calculation you can do. It's exactly counts the number of self-intersections of the walk. So we are just going to penalize the model using that. So the definition will just be with a parameter g, that is the parameter for repelling strength. We should define the weakly self-avoiding walk measure q and g just by this derivative. dq of dpn should be proportional to exponential minus g times the number of self-intersections, where the pn is the simple random walk measure. So this is a well-studied model. For g equals 0 is the simple random walk, and for g equals to infinity is the strictly self-avoiding walk. So in dimension 1, this model actually behaves, once you turn on a little bit of self-intersections, penalizations, this model behaves exactly like the strictly self-avoiding walk, in the sense that it actually escapes linearly from the origin, and it's going to have a asymptotically deterministic speed. So this is a theorem by Graeber and then Hollander in 1993, so more than 30 years from now. There exists an analytic function theta of g, which is just the speed of walk, such that for any parameter g bigger than 0, any epsilon tolerance, I have this weak law of large number type result. If I condition on my walk going to the right, this is just to break the symmetry of going left and right. My walk, or essentially xm divided by n, is going to converge to my speed theta of g. And this theta of g is between 0 and 1. So this theta of g is the speed of the walk, and of course by symmetry going to the left, they also have the same speed. And the long-standing conjecture is that this theta of g should be strictly increasing in the parameter g. And in some sense, if you have more repelling of your walk, the walk should just go away from the origin faster, but this is not known. And the main result of this talk, or this paper, is actually just that we prove this conjecture, but for a related model, which is just built on continuous time version of the random walk instead of the discrete simple random walk. So let me go with that, the definition. So already the only difference thing is that we just use a continuous time simple random walk, and the local time now is defined in terms of an integral instead of a sum. So we should integrate up to time capital T from 0 to capital T, the indicator for my walk to be at exactly the position x. Oh, by the way, this simple random walk is essentially that we have a Poisson clock, equally likely that we jump to the left and jump to the right, each with rate 1. And to define the model, we again have some parameter g bigger than 0, and this is notation phi of t should be t squared. This is exactly the L2 norm of the local time. And the weakly self-avoiding walk measure is defined analogously just by the expectation of the function, which is with respect to simple random walk weighted by this exponential e to the minus g. Should move my cursor out. E to the minus g times the sum of phi of local time. But my phi is just square, so this is really just the self-intersection time of my random walk. So this defines the model. And we actually treat more general models it really doesn't really rely on this thing being a quadratic. So we have certain assumptions that we need. The function phi should start at 0, should be differentiable, and this one is pretty crucial. Phi of t over t should be increasing, and with limit infinity. And this one is actually a technical assumption that's not so important. So for example, phi can be any polynomial with degree more than 2 with positive coefficients. So for example, if phi of t is t cubed, then we don't really penalize self-intersections, but we penalize triple intersections. So if the walk intersects itself 3 times at the point, we penalize that instead. How should I handle that? Okay. Anyway, so for this talk, really we should think about phi of t just being t squared. That's the self-intersection time. But the proof works more generally. And we see really the same behavior for all these models. So let me talk about the main result. The main result is exactly the same statement as the discrete time weekly self-forwarding walk, but we prove in addition that the speed, theta of g, has strictly positive derivative. So this statement is the same with the new thing being the theta prime of g. Oh, now the speed is actually between 0 and infinity. If you didn't notice, for the strictly, for the discrete time model, the strictly self-avoiding thing just has speed 1 going to the level, right? But now this thing actually can have any positive thing. And the new thing here is that the theta prime, we show it to be positive everywhere, which in particular implies it's strictly monotone in G. And our proof for the existence of speed actually is very different from discrete time case, and we use moments of x of t. The discrete time paper proved this speed using large deviation theory, which is a very different model. We are going to use the Laplace transform for this. So maybe let me talk about or maybe before that. So here's a numerical result on the theta of g. Of course, I tried this before I do any proof. So the dots here are my data points, and you can see it's really increasing in the g parameter. Let me go to the end-to-end distance result. So my notation, I will use this tilde asymptotic notation just to mean the ratio is going to converge to 1. And my theorem is that if I look at walks going to the right, and if I look at the endpoint to the k power, asymptotically that's going to look like theta of g times t to the power of k. And this works for any k integer. In particular, this is going to imply my xt over t, if we divide the t over, this is going to converge to theta of g in LP for any positive even p. So in particular, we get the convergence in probability stated in the last theorem, the main theorem. And actually, only the k equals 2 is enough for this convergence, but we prove it for any k. And we prove it using the Laplace transform and the new Tauberian theorem. So what we will do is that we will take the Laplace transform and get asymptotics in the frequency space, the Laplace space, and then we use the Tauberian theorem to pull back the asymptotics to the x space, or the time space. Once we prove that, the theta prime bigger than 0 part of the main theorem is actually proving using a separate argument, which uses stochastic dominance, which I will talk about. Maybe before everything, I should define some more notations. This 2-point function gij, or maybe before that, I should define pij, which is really just kind of, you should think about it, the transition probability from I to j in time t, but this one is not normalized. It's exactly the probability for the walk to go from I to j at time t, but with this penalty due to self-intersections. And for some mu in a complex, I should take the Laplace transform of this pij, and that Laplace transform, I call it the 2-point function of the weakly self-avoiding walk. So gij should be the Laplace transform of my pij, and then which has this nice form. It's written as an integral of the expectation of the product of p, with my p being my exponential weights. And writing in this form actually allows us to use some supersymmetric representation, which I will talk about more to handle the model. Here, positive nu will act as like a killing rate for the walk. So, but what we use, actually, we use just complex nu, and they will have real parts actually negative, just to cancel out some parts of the self-intersections, and that will actually show the critical behavior. And we also need nu to be complex because our Tauberian theorem is a complex one. But this is really technical restriction on the nu. For this model, it's actually very nicely dominated by real parts of the nu, so the complex is not really a problem. So if you put a complex nu here, it quickly drops out if you take the absolute value. It's just dominated by the real nu. So the two-point function Gij here actually can be represented using a so-called transfer operator, which I call Q, acting on L2 as this inner product. So my Gij is gonna be given by the inner product of Q to the power J minus I acting on some function F, and then inner product with F, when my nu is bigger than some critical nu. This is actually the crucial point that we use for the one-dimensionality. This Q to the J minus I is really just like I kind of have a transfer matrix that moves me from I to J. And the F is actually coming from the other two sides, the far ends of the model. So I have this inner product representation for my two-point function. And the critical point nu C is actually characterized by my operator Q having the operator norm exactly 1. It's something that we can get out of this model. Essentially, if the operator norm is less than 1, then this thing converges, and the two-point function will just decays exponentially in the distance. That's why it's subcritical. This is the characterization for the critical point. And this representation itself is proved using a supersymmetric version of the BFS Dynkin isomorphism theorem. Essentially, we have a representation of a system as kind of like a 5 to the 4th model, but it's supersymmetric, so we have both bosons and fermions, which I will not talk about. We just take that as granted. Let me get the asymptotics out of here. So using this inner product representation, Gij, if we sum over all the j's with I being 0, this gives the positive part, the right-hand side part of this acceptability, which is a sum that we can do. It's just a sum of a geometric series, so we just get Q times 1 minus Q to the inverse, acting on some F and F bar. And just by looking at this expression, there's one thing I forgot to mention. This function F here is actually regular at the critical point. So it doesn't really play any role in the asymptotics as nu goes to nu C. Yep.
So you are using an isomorphism theorem in order to prove
this representation.
This representation.
Yes.
And like this, okay, it doesn't sound. So this will be really your crucial input for the rest of your proof.
Yes.
And everything is kind of hidden here.
It's not quite. This representation is really just a rewriting of the two-point function in terms of a spin system.
But could I find a kind of elementary way of proving this representation? Or?
For the discrete time model, there's actually a similar, not quite similar here, but for the discrete time model, there's also a so-called transfer operator that looks very much similar. And all the properties are the same, but that proof doesn't really use any representation. And as I'm going to tell, this operator is really just acting on the local times at each point.
So how do you? So this F is some explicit thing.
It's some fixed point of some operator. Okay. Yeah. So it's some explicit thing that we can show is some regular at the critical point. It's essentially coming from two sides of the system. So the far sides, and then the distance being so long that it just becomes a fixed point of that operator. So it's a different operator than Q. but it's something that we can find. So to get the asymptotics, as I said, we sum up to get the chi. This is sum of the g's. And for the asymptotic, since f is regular at the critical point, what we get is just this linear divergence in this 1 minus q inverse. So what we get for the asymptotic as nu goes to nu c is some things over nu minus nu c. And using our Newton-Tauberian theorem, we can lift this back to the t space as t goes to infinity. I can look at my sum of p0j's weighted by e to the minus nu ct. This is going to converge to the same constant here. This is a classical Tauberian type theorem. And in general, for any k integer, I will look at the kth power, the kth moment of my G0j, and using the same representation of the G0j, I can actually get that, oh, I skipped the line, but we can actually get asymptotics of sum of j, the kth moment of P0j, which is gonna just look like some constant with the power t to the k. And using this, if I do the division to get my moments, it's just this expression. And you can see the u bar part comes from both the numerator and the denominator. And the tk just shows up here. And then this thing has the minus k plus 1 power. And the denominator has just 1 power. So we get this expression to the power minus k. This just identifies the escape speed as the inverse of this complicated thing that I haven't talked about. This is the derivative of the operator norm with respect to nu at the critical point.
So both f and q depend on.
Sorry?
So q depends on nu as well as f?
Yes. It doesn't depend on f, but depends on nu and g.
Sorry, f depends on nu and g, and
yes.
q depends on...
Yeah, everything depends on nu and g, yes. But f is regular at the nu c, so it doesn't show up in here. So this is actually how we identify the escape speed. And this same expression actually holds, for the discrete time model. So there's some transfer operator there also, and the speed is also given by some derivative to the inverse. So we are really having a very different proof, but really finding the same phenomenon for the two models. And then for the rest of the talk, I will just differentiate this theta of g, and then I will show it's positive. It sounds very easy. I should tell more about the transfer operator. This q is, from now, first thing, we should assume nu is real. And this operator q is just actually just given by some integral with respect to some kernel. This kernel is actually very nice because of all my p's are exponentially decaying. And then, it's just, the p's carry the self-intersection properties. And the rest of this is actually coming from the random walk, e to the minus t, e to the minus s, I naught, with some parameters. The I naught is the modified Bessel function of the first kind. This second part here is actually the Markov transition kernel for the local time of the continuous time simple random walk. This is the Ray-Knight theorem. So essentially, this operator is just acting on the local times of the walk. But we modified it by this penalty here due to the self-intersections. Sorry? Yep.
Is your formula, is this for the case of L squared or for general?
It's for general phi.
So where do the two, the t and the s?
It's just the t and s are kind of a local times at two neighboring points. And the 1/2 here is just that I put half of them on the left and half of them on the right to make this operator symmetric. So that's my transfer operator. And to prove the monotonicity of the speed, I will just differentiate my theta of g using the implicit function theorem. So this is some calculus. I should differentiate and get some mixed derivatives. Well, first of all, my theta of g, or the inverse of theta of g is just the derivative of norm of q in nu. If I write my lambda as the norm of q, so if I differentiate in g, I get the cross derivative nu and g, subtracted the double derivative nu, with the chain rule being the derivative of nu c in g. And after some calculation, we'll see that what we really need to show is this combination of mixed derivatives to be positive, because this denominator here is positive. So what we will do is to show this combination to be negative, sorry. And of course, it's hard to differentiate the second derivative of some eigenvalue. I didn't mention. Yes, my operator norm here is actually the leading eigenvalue of my operator. Just because the operator is very nice. And the idea here is that it's hard to find, so we should use some approximation. And the easiest way to find the leading eigenvalue is just to operate my operator on some function f. This is any f, and then take the nth root of that the result. That should give my leading eigenvalue. And I have a lemma that says that we can also do that to the second derivatives. And the result is that if we pick the f to be the leading normalized positive eigenvector of my operator q, then I can use this and I can differentiate this to the second derivatives. And the combination I get, there's some explicit calculation that I can do. And after that calculation, what I get is that the result I want is given in terms of series. Is some term minus C0 with some series in Cn, where my Cn is some explicit thing that I can calculate. Here, you can kind of see it from here. This is in the form of my operator n times acting on some functions. But now they don't act on the h naught or the f there, but they act on t times h naught. The t is for taking the new derivative. And on the other side, it acts on the phi of s times h naught, which is for taking the g derivatives. And this term really comes from the cross derivatives of the lambda in nu and g. And this term here comes from one pure nu derivative. This term here comes from the two derivatives in nu. And this term here comes from the pure derivative in g. So using this lemma, what we will do is that, remember, what we want to show is the L of lambda is negative. So what we do is that we will prove C naught to be strictly negative. I mean, C naught to be strictly positive, so this term is strictly negative. And we will prove every one of Cn is weakly positive, so this term is weakly negative. And when we sum them up, I get some negative thing. And the trick here is actually to rearrange my Cn. So if I go back, so once I rearranged my Cn like this, so Cn bigger than 0 is equivalent to this thing, this inequality. So the Cn is defined in terms of this term times this term minus this term times that term. So I just did some rearranging here. But the good thing about rearranging it like this is that I can actually write both sides as some expectation of some random vector. And then if I can show the two random vectors dominate each other, then I can get the expectation to be bigger than the other side. How long do I have? 5 minutes. Probably I can do the C naught part. And the C naught part, let me go back. And let me do the C n equals 0 case. If n is 0, then my q completely drops out of the equation. And what I get is just the product of t times h naught times phi times h naught for the left-hand side here. So the thing I need to prove is that I have a s times phi times h naught squared ds over some other things that are just there. To prove this inequality, I should just define my random variables x and y just by the density functions. For the left-hand side, I should really put this phi of s h naught squared of s as my density function, and the denominator here is just the normalization factor. And then the expectation of this random variable y is precisely the left-hand side of the inequality. And I do the same thing for the right-hand side, but now this times the density function is s times h naught squared of s. I want to prove that they dominate each other. Y dominates X. I would just look at the ratio of the density functions. Up to some constants, this is just phi of S divided by S, which is assumed to be increasing, as one of the main hypotheses. So the ratio of density functions being increasing implies Y dominates X, and therefore I get the expectation of Y being bigger than the expectation of X, which is this inequality here, without this strictly thing. And the strict inequality actually follows from my H0 being strictly positive everywhere. So they are actually different distributions, so they don't, the expectations don't coincide. I have 3 minutes, but let me probably just stop here. Yeah, then I can go through the C1 part. This is the last slide, anyways. I should show the C1 slide because this is really some place that actually uses the continuous time nature of the model. I'm just gonna do this random vector for this instead of one-dimensional thing. I have two-dimensional thing, 2 components, but I already played the same game. For the left-hand side of my goal, or the numerator here. So essentially, I will define my random vector y of 2 component to be this. I have h0 of S1, my kernel that relates the 2 components, and then times the phi of S0, h0 of S0. So that if I look at the expectation, which brings of the first component, S1, that will create exactly the left-hand side of the inequality that I want, which is here. So the expectation creates an extra S1, and the rest I put it in the density function. So question? No? And then for the right-hand side, I play the same game, but the only difference is that instead of phi of S0 here, I put S0 here. So both sides of the inequality still are expectations of random vectors. And then what I will do is that I will show X is dominated by Y. Again, this implies expectation of Y1 is bigger than the expectation of X1. And using my H0 being an eigenvector of Q and the C0 proof, the zeroth marginal actually dominates each other. X0 is dominated by Y0. This is essentially just because if we integrate out S1 here, we get the integral of H0 with the kernel K, which is just Q acting on the H0, and H0 is an eigenvector, so it drops out. So what I get is exactly S0 times H0 of S0, which is the C0 case. So this zeroth component is actually very easy, and we only need to prove domination of the conditional distributions. And so here are the conditional distributions for my X1 conditioning on X0, and my Y1 conditioning on Y0. And I will just take the ratio of the 2 density functions and show a smaller one in S1. So here's some expression for the ratio. And you see lots of terms are just constants in, for example, here in Y0 or in X0, so they don't really play any role in the conditioning. So when I take the ratio, what I really get is the ratio of my kernel, integral kernels. And here's the explicit expression for it. And it boils down to a ratio of my modified Bessel function with different parameters, Y0 being bigger than X0. Therefore, what we do is just that we show this thing is strictly increasing in S1 using some known properties of the modified Bessel function. What we do is actually we take the logarithmic derivative of this function and show it's positive. That shows the ratio is increasing in S1. Therefore, the conditional distributions dominate in the right way, and concludes the proof for the C1 case. And I hope I have convinced you that the general Cn case is similar. We just get n+1 dimensional vectors instead of n dimensional ones. So let me stop there.
Other questions?
So you do a lot of explicit calculations, so maybe this seems scary, but what would happen if you did it on a strip? And could you say something about how the speed depends on the width of the strip?
Width of the strip.
Yeah, so instead of doing it on the line,
on
do it
line
on
on
a strip of width L.
I think it's more or less because when I got that representation 2. Let me probably do it again. But on the strip, I think maybe more complicated than on the line. Sorry for that.
You don't always get backwards without going through.
But I think it will still have.
Yeah, on the strip, we still have an expression like this, but we get the different f on the left and right, and they depend on the position of the ing. Yeah.
So I agree it will be harder.
Yeah.
But it would be interesting if you could say something about how the speed depends on the width of the strip.
That's interesting. I haven't thought about this. Maybe I think it's probably doable because we can compare the two models just by because it's the same, really the same field. Just that the f is different from the f on the strip. Yeah, doesn't it even have the strip? The strip.
You can go along center strip just with 2.
I think it's not gonna. It's recurrent. I mean, it's restricted to the strip, so it doesn't really go away.
So do you know what happens at g equals 0?
As g equals 0. Yes, I think it decays at the speed decays as a cubic.
Sorry?
It says it's a cubic decay near 0. It's known for the discrete time model. It's proof in some paper that I can give you reference of. But for this model, I didn't really try to show the asymptotics as g equals 0.
So, I mean, it's a bit. So, can you say what happens to theta prime as g approaches 0, or?
Theta prime. I didn't try to do it, but I think maybe it doesn't seem out of reach calculating the theta prime.
And related, so I think you mentioned that somehow, your picture indicates that theta double prime has a sign, right?
Right.
It's complicated. So
yeah, the double prime looks even harder, but theta prime is for it.
Because one naive thing is if you prove that theta prime is positive the way you did by showing that one expectation.
Right.
Oftentimes, if you want to prove that theta double prime is say less than or equal to 0 or whatever, it amounts to showing that some covariance is non-negative or something.
Right.
So you can maybe phrase it.
Yeah, I think it's a good question to ask because we have all things that we did here. It could be possible that to calculate theta double prime. Yes.
Other questions?
One last
Yeah.
one. This curve here,
Yeah.
is this something that is fitted or you actually know with that?
Oh, the blue ones are what I calculated.
So the blue ones are simulated?
Yeah, the blue ones are simulated.
And the red one?
It's just interpolated.
It's just interpolated.
Yeah.
So you don't know, I mean, it looks sort of like a, I guess you said it's a cubic square distance.
Yeah, it's cubic for the discrete model, so it should be here. I mean, cubic root.
Yeah.
But you don't have a conjecture or formula for theta.
A formula for theta.
Yeah.
I mean, this. Oh, wait. Theta.
Like you would like to have theta of g equals something.
We do have that, right? It's the thing that we differentiate. It's the derivative of the operator.
No, but I mean formula in terms of g.
In terms of g.
Yeah.
I mean, the operator is in terms of g. It's not some explicit thing.
Yeah, exactly.
We're getting asymptotic is probably possible.
G to the 1/3. Yeah, it's a good formula.
Other questions? Okay, it does not seem to be the case, so let's thank this